Guys, and welcome to the second part of this particular past question. And in this particular past question video review, we are going to actually solve for the second part, which is we have to write out the first few terms of j 1 over 2 of x from the above, and we should prove that j 1 over 2 of x is equal to root 2 all over pi x sin x. So the method I'm going to use might be a little bit long, but I want you to understand why my methods are long, not necessarily because they are long, but because I'm explaining them. So if I were to solve it on my own, I'll be a little bit faster than usual, but once I'm explaining it, I try to explain to you so that you can understand. That's why it's a little bit too long. So try to watch, and I hope you understand. So let's dive into the solution for this particular question. So we're going to write the first few terms of j1 over 2 of x, and we are going to prove that j1 over 2 of x is equal to the square root of 2 all over pi x then sin x. So let's dive in together. So solution. So the b parts, so the first few terms of j half of x, that's Bessel function of the first kind of half order. Okay, so in this particular part, you need to recall that our j n of x, that's our n order Bessel function, is x over 2 all raised to the power of n. We now have summation m equal to 0 down to infinity minus 1 raised to the power of m. And I have x raised to the power of 2m all over 2 raised to the power of 2m. I have m factorial. Then we now have gamma of what? We have m plus n plus 1. So this is the gamma function that I believe most of us are familiar with. So if we want to write out the expression for j1 over 2 of x, we can actually decide to modify this formula a little. So to modify it a little, we can actually say our j n of x is still the same thing as x over 2 raised to the power of n, and we now have open, or let's just stick to our summation, m equal to 0 then down to infinity. Then I'm going to take these two out. All right, I'm going to take them out to the farthest right, and I'm going to be left with minus 1 m all over. You have m factorial, then you have gamma of m plus n plus 1. Then you now have x over 2 all raised to the power of 2m. Okay, by law of indices, a over n divided by b over n is a over b all raised to the power of n. So I hope you remember, and that is why I did this over this is still the same thing as x over 2 raised to the power of 2m. So this will now give me what I'm going to use as a yardstick to find my j of x, that's in terms of n being 1 over 2. So let me go to another page of the screen, and I'm going to copy this out now. Okay guys, so we stopped here previously, and we understood how I got to this point. So in order to get my j of 1 over 2 in this form, j1 over 2 of x, you can now say it is equal to x over 2 all raised to the power of 1 over 2, and you now have sigma m equal to 0 into infinity, and you now have minus 1 to the m, and you now have m factorial gamma of m plus 1 over 2 plus 1, okay, for n being 1 over 2, and you now have x over 2 raised to the power of what? 2. I want you to notice something special about this formula for Bessel's functions of the n order of the first kind. In this summation, that's in this summation place, there is only one spot for you to put n, to plug in this n over here, and that is at this point, okay? So other things, all this m you're seeing is just our counting variable, which in this case is m. Okay, so let's work with it and see what we get. So this is going to translate to j1 over 2 of x is equal to x over 2, then you now have 1 over 2, then you now have sigma m equal to 0, infinity minus 1 to the m, and you now have m factorial, then gamma of m plus 3 over 2, then you have x over 2 raised to the power of 2m. Now 1 over 2 plus 1 is 3 over 2, so somebody can start expanding like this. So I'll have x over 2 half like this. Then if we start expanding, we will start with substituting m equal to 0. M is 0, 1, 2, up to infinity, like that. So when m is equal to 0, okay, x over 2, then 2 times 0. 2 times 0 is 0, so x over 2 raised to the power of 0 is 1. So minus 1 raised to the power of 0 is 1. 0 factorial is 1. So what I have in this particular first position is I'll have 1 all over gamma of 3 over 2. Is that okay? So 1 over gamma of 3 over 2. So that's for m equal to 0. Then when m is equal to 1, okay, then you have minus 1 raised to the power of 1, which is going to be a negative. So you now have 1, and all over 1 factorial is 1, okay, and gamma of 1 plus 3 over 2, this is the gamma of 5 over 2. Is that okay? And you now have x over 2 raised to the power of what? 2. Okay, so we'll go in that line. So the next one is when m is 2. So I'm going to stop at m is 2, and you can try to figure out the rest for yourself. So when m is 2, I'm going to have minus 1 raised to the power of 2, which is a positive 1. So plus 1 all over. Then you now have 2 factorial. Okay, I can just put it like this, 2 factorial. Then gamma of 2 plus 3 over 2. 2 plus 3 over 2. So 2 plus 3 over 2 is definitely going to give you 7 over 2. Is that okay? So you can notice 3 over 2, 5 over 2, 7 over 2. You can easily spot that this is a pattern of repetitive, the pattern of odd numbers from 3. So this one is going to be x over 2 raised to the power of 4. Okay, so it keeps increasing, so the next one will be minus dot dot dot. So this is like an expansion for j1 over 2 of x. So someone can leave his j1 over 2 of x in this form, so you don't need to simplify further. You could just leave it like this. So the main work is actually in the second part of this video, which we want to actually dive into now. So let's dive into it. So the second part is we now want to prove that j1 over 2 of x, okay, sorry, that was my alarm. j1 over 2 of x is equal to square root of 2 all over pi x, and we now have sine x. So guys, this is the main part of this video, and we are going to show that the Bessel's function of the first kind of half order, that's j1 over 2 of x, is still the same thing as the square root of 2 all over pi x multiplied by sine x. So how we are going to go about that is we need to make some certain retrospections on what we've actually done in the past. So you need to make some remembrance, or you need to recall that for a function like sine x, the power series expansion is given to us as summation m equal to 0 down to infinity, and you now have minus 1 raised to the power of m. You now have x raised to the power of 2m plus 1 all over 2m plus 1 factorial. Okay, so this is the power series expansion for sine x. So also you have to recall one of those formulas that I taught you in the past. That's the blessed formula for gamma function of positive half integers, and in one of those videos that I defined in the past, you could check it out later, but I was able to come up with a formula to generalize the gamma function of n over 2, and that formula is going to be very handy in us achieving the proof of this particular function above. So gamma of n over 2 generally is defined as the square root of pi all over, you now have 2 raised to the power of n minus 1 over 2, and you have to multiply by the product operator. That's the product of all odd numbers between I equal to 0 and I equal to n minus 3 over 2, and this is 2i plus 1. Okay, so this is another representation for gamma of n over 2 according to how I derived it in that formula. Now we are going to use these two tools to actually resolve this particular enigma over here. So let's go about it step by step so that you see how to solve it. So first of all, we are going to rewrite our j of n so that everybody will take it. Let's just take it from scratch. So our j of n, okay, that's our jn of x, that's the Bessel's function of the first kind of n order, is defined as x over 2 raised to the power of n. Okay, and you now have summation m equal to 0 and infinity minus 1 raised to the power of m, x raised to the power of 2m, and divided by, you have 2 raised to the power of 2m, and you now have m factorial, and you now have gamma of m plus n plus 1. Okay, so this is your Bessel's function of the first kind of order n. So having it like this, you can now say your j of x, that's 1 over 2 when n is 1 over 2, is going to be x over 2 1 over 2. Anywhere we see n, we'll replace it with 1 over 2, 0 down to infinity, and you now have minus 1 to the m, you have x to the 2m, and over 2 to the 2m, m factorial, then you now have gamma of m plus 1 over 2 plus 1. Okay, so this is how we have replaced this one. So the next thing to do is j 1 over 2 of x is x over 2 raised to the power of 1 over 2. You now have summation m equal to 0 infinity minus 1 to the m, x to the 2m all over 2 to the 2m, m factorial. Now have gamma of m plus, when you simplify this, you're going to get 3 over 2. Is that okay? So this is what we have for our j 1 over 2 of x. So the secret of actually getting the solution to this problem actually lies in this part of this formula. So let's consider gamma of what? M plus what? 3 over 2. So we are going to consider gamma of m plus 3 over 2. Now if you consider gamma of m plus 3 over 2, it's still the same thing as you writing gamma of 2m plus 3 all over 2. Okay, when you simplify by LCM, 2 times m is 2m plus 3, then everything divided by 2. Now we are going to use this particular formula that gamma of n over 2 generally is equal to what? Root pi divided by 2 to the n minus 1 over 2. Okay, then everything multiplied by pi, that's the product operator from I equal to 0, then you now have n minus 3 over 2, and you now have 2I plus 1. So we are going to use this formula to resolve this over here. So in using this formula, our gamma of 2m plus 3 over 2 can still be expressed as root pi all over 2 into, so wherever I see n, I'm taking 2m plus 3 to act as n. So you have 2m plus 3 minus 1 all over 2, and you now have pi from I equal to 0 down to, you do the same thing here. This will be 2m plus 3 minus 3 over 2, and you now have 2I plus 1. Okay, so when you simplify further, you have 2m, okay, plus 3 over 2. That's the gamma of 2m plus 3 over 2 is root pi all over. So let's see what happens. We have 2 raised to the power of 2m. Now 3 minus 1 is 2, so I have 2m plus 2 over 2, and I now have my product operator from I equal to 0. Then you have plus 3 minus 3 is 0, so I just have 2m all over 2, and I have 2I plus 1. Okay, so if we have it in this way, we'll now have our gamma of 2m plus 3 over 2 is equal to pi all over 2. Now if you simplify, 2 can cancel out, leaving you with m plus 1. Okay, then we'll now have the product operator, 2 cancelling out to have m, so I equal to 0 to m, so we'll now have 2I plus 1. So this is the expression for gamma of m plus 3 over 2, which is still the same thing as gamma of 2m plus 3 over 2, and it evaluates to what? Root pi all over 2m plus 1. Okay, then taking the product of all odd numbers, the first m odd numbers. So if m is a particular integer, this pi from I equal to 0 to m means that we want to find the product of the first m odd what numbers. So this is still the same thing as you writing pi from I equal to 0 to m, that's 2I plus 1. Okay, someone else might expand it and he will have something like root pi all over 2m plus 1. So this stuff, the expansion is all the product of the odd numbers between 1 and m. So you have 1 on the first m odd numbers, not all the product of the odd numbers between 1 and m, sorry, the first m odd numbers. So you have 1, you have 3, 5, 7, then we are going to stop when I is m, we'll stop at 2m plus 1. Okay, so this is the product of the first m odd numbers, 1, 3, 5, 7, 9, and the last number odd number will be 2m plus 1. Okay, so this is the expression for gamma of m plus 3 over 2. Okay, so let's keep it handy. So another thing we want to do is in this particular denominator, now that we have used my formula that I derived in the previous video to expand the gamma of m over 2, another thing we want to consider is how does this term now interact with these two. Okay, so we are going to do that shortly. So we have already seen that the denominator is, you have consider the denominator. Considering the denominator, you have a 2 raised to the power of 2m, you have an m factorial, and you have a gamma of what? M plus 3 over 2, which we have already resolved to this particular term over here. So let's see how this one and this one interact with each other. Okay, and let's see what is going to happen, okay, from the interaction. So I am going to go to a new page. So in saying that, we have previously, we are considering the denominator, okay, or let's just write it that our j 1 over 2 of x is still the same thing as x all over 2 raised to the power of half. Okay, if you can remember the formula, then you now have sigma m equal to 0 down to infinity minus 1 to the m. Then we now have x to the 2m divided by 2 to the 2m, m factorial, and you now have gamma of m plus 3 over 2. Okay, so from which we actually found that gamma of m plus 3 over 2 was still the same thing as root pi all over 2 raised to the power of m plus 1. Okay, and you now have the product of all the first m odd numbers, which is still the same thing as you having 1, 3, 5 dot 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 up to 2m plus 1. So this is the expansion. Someone else can still write it the other way, pi all over 2m plus 1. Then you start with 2m plus 1, and the odd number before 2m plus 1, you find out that it is 2m minus 1, but we keep going down until we get to 3 and let's say 5, 3 and 1. Okay, so that's what it means. Now we also want to now consider how does these two terms interact with this term over here. So what you're doing is you have 2 raised to the power of 2m, and you now have m factorial multiplied by your gamma of m plus 2. So this, let's say this implies that is going to be, you have 2 raised to the power of 2m. Okay, so 2 raised to the power of 2m, then we'll have m factorial. So I'll be solving it gradually so that we'll understand what is happening. Then I'm now going to replace this with this expression over here. So I'm now going to have root pi and all over 2m plus 1. Then the product of odd numbers, 2m plus 1, like this. And you keep going down. In fact, the odd number that is before this one, okay, the odd number that is before this one is going to be the odd number that is before this one. Remember that how we actually got this stuff is when you took from I equal to 1 to m, 2i plus 1. So the last odd number is 2m plus 1. That means, sorry, this is I equal to 0, sorry. So the last odd number is what? 2m plus 1. So the one before it is when m is 1 less. That's when m is m minus 1. So if you substitute it into this formula, you have 2 into m minus 1, then plus 1, which is 2m minus 2 plus 1, which is 2m minus 1. Is that okay? So the odd number that is preceding this one is actually what? 2m minus 1. Now, from our knowledge of odd numbers, we know that odd numbers are always separated 2 from each other. So if you remove 1 from this, if you remove 2 from this one, you get minus 1. If you remove another 2, you get 2m minus 3. Is that okay? And it keeps going until we get to 5 times 3 times 1. Okay, so that's the concept and that's the logic of odd numbers, the product of the first m odd numbers. So the product of the first m odd numbers is from 1 to 2m plus 1. Please take note of that. So how do, or what will this reduce to? So this is still the same thing as you having now. These two can actually interact with each other. It will be 2 to the 2m, and you now have m factorial, you now have root pi, and all over. If you separate this one, you have 2 to the m dot 2. Okay, 2 to the m dot 2 from law of indices. Then we now have our 2m plus 1, 2m minus 1, and so on and so forth. Okay, down to 5, down to 3, and down to 1. Okay, so from law of indices, these two will actually cancel out, and you'll be left with 2m minus m. Then I can bring the root pi forward over 2. Then I can now bring my m factorial, and I can now bring 2m plus 1, 2m minus 1, 5, 3, 1. So you can see that this will now become root pi over 2. I'm just rearranging it randomly. Which one should come first? Okay, I feel m factorial should come first. Then this one, 2 raised to the power of 2m minus m, which is 2 raised to the power of m. 2m minus m is actually what? 2m. So you have it like this. So anyhow you arrange this one, it doesn't really matter, but I'm just trying to bring the constants first. So you have the product of the first m odd numbers, which is 2m plus 1, 2m minus 1, and so on and so forth, down to 5, 3, 1. So we're making progress, right? So you have your root pi all over 2. Then now here is where we're going to use some logic. So m factorial, everybody knows that m factorial, or let me bring 2 raised to the power of m first. M factorial is m, okay, m minus 1, and so on and so forth, down to 2 and down to 1. So when you multiply all numbers from m to 1, okay, that's your m factorial. Okay, then this is the product of our first m odd numbers. That's the 2m plus 1, the 2m minus 1, and so on to 5, to 3, to 1. Okay, so what are we having? Now, to solve this particular equation, you need to understand that from 1 to m, there are m terms. So 1, 2, you're multiplying m terms with each other. Similarly, from 1 to 2m plus 1, there are m terms, because this is actually the product of the first m odd number. So I'll write this as m terms. So there are also m terms here. Okay, m terms here. And when you have 2 raised to the power of m, take note, it's still the same thing as you separating 2. Okay, separating 2 m times. So when you spread 2m times, you have 2 raised to the power of m. So the reason why we need to spread 2 is in this next step over here. When we spread 2m times, we are going to use each of the 2's to multiply 1m. So 1 2 will multiply the first m, giving you 2m. Another 2 will multiply the next one, and to give you 2m minus 2. Another one will multiply the next one, maybe it will be 2m minus 4, and it will keep going until instead of us to get to 1, we will now have 4 and 2. Is that okay? So this 2 raised to the power of m has been spread m in m multiples of 2, and each of them have multiplied the corresponding m here. 1 2 for this m, another 2 for this term here, and so on and so forth. Is that okay? I hope you understand that. So everything there is multiplied by the product of what? The first m odd numbers, and so on and so forth. We have 5 3 1. So it now means that if you examine it closely, we are still dealing with our 2 raised to the power of 2m, our m factorial, and our gamma of m plus 3 over 2. So what does it translate to? So it translates to root pi over 2. Then now if you look at these terms together, if you now combine these two products, you will discover that this is the product of the first m odd numbers, and this is now like a factorial. Okay, factorial. Factorial, it was formerly m factorial, but because we spread 2m times, it's now like even factorial. So when you merge even factorial and odd factorial, you will discover that you will get something amazing. So if I start with 1 here now, okay, I'm going to start with the end. I'll start with 1, then I can now put 2, okay, and I can now put 3, okay, then I will now put 4, okay, from this side. I'll now put 5 from this side. I'll keep going like that. So I'll put 2m minus, before 2m minus 1, before 2m minus 2, okay, you have 2m minus 1. So 2m minus 1 comes first. Okay, so you have 2m minus 1, then from here, then 2m minus 2. Okay, so it will keep going like that. Then we'll now have, from this place, we'll have 2m, then finally we'll now have 2m plus 1. Now, if you observe these numbers very well, this is all even factorial, and odd factorial. So even factorial is the product of the first m even numbers, and odd factorial is the product of the first n odd numbers. Okay, so if you merge two of them together, you see that this is what we have, and this translates to pi over 2, and your result is going to be 2m plus 1 factorial. So voila, are we together? Now, the product of these two translates to what? 2m plus 1 factorial. So the summary of all these things that we've been doing, as you can see, 2m plus 1 factorial. After 2m plus 1, the next one will be 2m. It's, you know, factorial is about reducing 1 and so on and so forth. So these two combines to give us 2m plus 1 factorial, as we've seen. I hope you're going to look at it and learn how to do it yourself. So the whole denominator translates to just pi over 2, then the product of what? 2m plus 1. So that is what we want to do now, and actually find the simplification of our solutions. So even though you might not necessarily need to show this proof in your exam, I believe that you should know what this denominator translates to. Is that okay? So then for j of x, that's the half order, you have x over 2 to the 1 over 2, then sigma m equal to 0 to infinity minus 1 to the m, you have x to the 2m all over 2 to the 2m, you now have m factorial, then finally you now have what? Gamma of m plus 3 over 2. So you can now see when you get to this point, but by formula, okay, which we have already derived. If you have time to derive it, feel free. If you don't have time, please just memorize what this translates to. 2 raised to the power of 2m, then m factorial, then gamma of m plus 3 over 2 translates to root pi over 2, and you now have 2m plus 1 factorial. Okay, so when you have it like this, the next thing that you're supposed to do is you now substitute it back into the formula. And when you substitute it back into the formula, you have your j1 over 2 of x as x over 2 raised to the power of 1 over 2. Then you now have summation m equal to 0 into infinity minus 1. And you now have x to the 2m, and you now have divided by, so instead of you to have this, you're now going to have root pi over 2. Are we together? And you now have 2m plus 1 factorial. So we're getting somewhere, right? So the next thing for you to do now, from experience in solving this particular question, is you need to introduce something that is unusual to this formula. So before we do that, let's just simplify a little, and I'll show you when we have to introduce that. So j1 over 2 of x is going to be x all over 2 to the 1 over 2. Then you now have, if you remove this guy, since it's a constant, you can bring it out from the summation. It will be 1 all over root pi divided by 2. Okay, and you now have summation m equal to 0 down to infinity. I have minus 1, and you now have x to m all over 2m plus 1 factorial. Is that okay? So let's simplify this hand. You have g 1 over 2 of x is equal to x all over 2 raised to the power of half. So if you translate this, you get 2 all over what? Root pi. Is that okay? 2 over root pi. Now, immediately we translate this, we are going to do something. We are going to have an x inverse, then we'll now have an x. And I'll explain the necessity of introducing this. Of course, f in x raised to the power of minus 1 times x will give you 1. So if there was a 1 here, that one has translated to x inverse, then times x. You now have m0 to infinity. You have minus 1. Then you now have x to the 2m all over 2m plus 1 factorial. So the next thing you're going to do, okay, is you're going to take one of these x and you send it into the summation. So it is possible for us to send the x into the summation, x raised to the power of 1 into the summation, since this x is not really having anything to do with this variable m. So it's like having a constant power. So I can actually carry this x and I can put it into this summation. So this is how I'm going to do it if it were me solving. Okay, I have what? X over 2 all raised to the power of 1 over 2. I can change this one to 4 all over pi raised to the power of 1 over 2. And you'll discover that it's still the same thing. So you can see that this is still the same thing with this. So the reason is when you have 2 all over root pi, it's still the same thing as you having what? The square root of 4 all over the square root of pi, which is, according to sword, is 4 over root pi. So 1 root 4 over pi. So this is the concept of me translating this to this. And 4 over pi also in the square root symbol is still 4 over pi raised to the power of 1 over 2. Is that okay? So having it like that now makes it easy for us to make some cancellations. We can make some cancellations like this. j 1 over 2 of x will now be, you match these two by indices, a n b m is still ab all raised to the power of m. So this 2 is x over 2, then 4 all over what? Pi all raised to the power of 1 over 2. And I'll save one x, that's this particular one, while I'll send the other one into the summation. Minus 1, and you now have x 2m dot x. So this x has now been translated into this place. You now have 2m plus 1 factorial. Are we good? So at the end of the day, you have j 1 over 2 of x is equal to 2 here 1, 2 here 2. So you now have 2x over pi into 1 over 2. Then you now have x inverse summation m to 0 infinity minus 1. I missed an m here, sorry about that. When did I miss the m? I missed it from these points. Okay, so I hope you wrote it in your own. Then minus 1 to the m, you have from indices, these two will be 2m plus 1 all over 2m plus 1 factorial. Okay, so if you are very sensitive, you will see that this one is already the power series expansion of sine x. Okay, but before we get there, let's just simplify this one and see what we get. So this is j 1 over 2 of x is equal to, I'm going to separate this, and I'm going to separate it as, because I want to match the x's together, or how else can I do that? If I want to match the x's together, alright, see, let's do something intelligent. So this is still the same thing as you having 2x over pi. Okay, follow me, 1 over 2. And if you want to convert this one such that it has a power of 1 over 2, you can say x raised to the power of minus 2, then 1 over 2. I hope that makes sense. So minus 2 cancel out these two is 1, then 1 times 1 will now give you your minus 1 back. So you have m equal to 0, infinity minus 1, m 2 to the 2, okay, this is not 2, this is x to the 2 m plus 1 over 2m plus 1 factorial. Okay, so if you solve j1 over 2 of x will be, you can now match these two together since they have the same power. You have 2x all over pi multiplied by, okay, x to the minus 2, everything is 1 over 2. You now have m to the 0, infinity minus 1 to the mx to m plus 1 all over 2m plus 1 factorial. So you now observe that this will translate to 2x minus 1. So x1 times x to the minus 2 will give you x minus 1 over pi. Then you now have 1 over 2. Then you now have summation m to 0, then infinity minus 1 raised to the power of m, and x raised to the power of 2m plus 1 all over 2m plus 1 factorial. So this is still the same thing as you having what, if you rearrange this with law of indices, you get 2 all over pi x, okay, raised to the power of 1 over 2. Then from power series expansion of sine x, you get this, so you replace it with sine x. You can now say therefore j1 over 2 of x is still the same thing as you having, from indices, anything raised to the power of 1 over 2 is square root, so you have 2 all over pi x multiplied by sine x. So that's it. So this is the proof that the Bessel's function of first kind or half order is still the same thing as 2 all over pi x. That's the square root of 2 all over pi x, then multiplied by sine x. Now, if you use the same concept that I've taught you, you should be able to prove that j of minus 1 over 2, okay, that's j minus 1 over 2 of x will give you root 2 all over pi x cos x. So I want you to figure out how this one became like this by yourself. If you can't figure it out now because of the constraints of time, maybe later on in your convenience time, but I'm going to still use this concept to make that derivation for us much later. So what are the key things to take note of? Apart from the lengthy explanation I had to do over here, okay, in deriving this formula, if you understood this particular method that I explained over here, it's good and fine for you. But what I'm going to suggest is maybe in an exam scenario, because of time, what you just need to do is to make a statement. So when you get to this point, okay, make a statement that this denominator is going to translate, okay, this denominator is going to translate to this. So this denominator translates to this expression over here. Okay, that's pi all over 2 and 2m plus 1. So you said this denominator translates to this from our knowledge of beta gamma function, sorry. So the whole of this denominator translates to this. So when the whole of this denominator translates to this, then that's when you can now replace the whole of this denominator with that expression. Okay, you replace it with that expression, then you now start simplifying. You simplify gradually, simplify. As you're simplifying, have in mind the power series expansion for sine x, which is summation m equal to 0 infinity. Then you now have minus 1 raised to the power of m. You have x to the 2m plus 1 all over 2m plus 1 factorial. So as you're simplifying, have that at the back of your mind. So that was what made me to introduce this particular term over here, x inverse, then multiplied by x. So this x inverse will go and interact with the terms over here, while this x will go and interact with the term in the summation. Okay, so when you do that, you're going to get all of this eventually, and you now get to your final answer over here. So the most important thing is what? Making that statement that the denominator of our Bessel's function translates to root pi all over 2 then times 2m plus 1 factorial. So I know this video was quite lengthy, but I hope you like it and you subscribe to my channel, because I'll be showing you a lot of things that you need to know in mathematics. And I am still going to solve the last part, and hopefully you're going to understand it too. So the last part of the question will be for us to find the solution to the third part, which is to prove that the Bessel's function of n plus the Bessel's function of minus n is equal to 0. So stay tuned, and till the next video, stay blessed. Yeah, bye.